Доброе утро всем, кто собрался. Слышно меня?
Доброе утро, да, слышно.
Так, ну хорошо, наверное, можем начинать, если нет возражений. Надеюсь, все, кто хотел, собрался или почти собрались. Хорошо, значит, сегодня мы с вами продолжим говорить про разные платформы реализации квантовых компьютеров. Вот. И в первой лекции, двойной лекции, мы говорили об общих вещах, как бы связанных с построением квантовых процессоров, ну и конкретно разбирали пример ионов в ловушках. Значит, это атомы с отобранными электронами, которые имеют заряд, поэтому их можно контролировать очень интересным, красивым образом в электрическом поле. И вы помните, что мы говорили, что для этого требуется использование как переменных полей, так и постоянных полей. Вот. Значит, сегодня у нас план поговорить в первой лекции про нейтральные атомы и фотоны и перейти к дефектам в кристаллах, значит, о которых мы будем с вами говорить. Дефекты в кремнии, дефекты в алмазе. Вот. Ну и дальше посмотрим, сколько всего мы успеем. В принципе, я планирую за сегодняшний день, то есть за 2 лекции, более-менее это введение в несруководящие системы закончить. Вот. То есть надеюсь, что мы сможем с вами сегодня поговорить про квантовые точки. Ну и, может быть, еще упомянуть электронные поверхности гелия, хотя это, в общем, как бы тема, которая, ну, может быть, была сильно интересна, скажем так, лет 10-15 назад, даже, наверное, 15-20 назад, когда не было еще, скажем так, победителей в этой гонке по реализации железа для квантовых компьютеров. Вот. Но как бы это вот физическая идея очень красивая, но, конечно, как бы в этой гонке выявились победители, о которых в основном будем говорить. Сверхпроводники, ну и в том числе, конечно, ионы атома, о которых мы тоже сегодня говорим. Но электроны на поверхности жидкого гелия, ну, до настоящего момента являются скорее такой более экзотической формой, значит, реализации квантовых кубитов. Хорошо. Да, забыл спросить, есть ли какие-то вопросы по прошлой лекции? Может быть, сразу у кого-то что-то осталось? Желание спросить. Если нет, давайте тогда будем двигаться. Так, чат пустой. Хорошо. Значит, сегодня поговорим для начала о квантовых вычислениях с использованием нейтральных атомов. Значит, нейтральные атомы, они, понятное дело, имеют одинаковое количество протонов и электронов, и поэтому заряжены нейтрально, то есть у них нет заряда, и поэтому, в общем-то, их особенностью и преимуществом является то, что они очень слабо связаны с окружением. То есть они не взаимодействуют в первом порядке с внешнеэлектрическими полями. Конечно, их можно подрисовать, и это тоже как бы является важной частью реализации, значит, платформы, важной частью этой платформы реализации квантовых битов, но, тем не менее, с постоянными полями народными они не взаимодействуют. Вот. Значит, с атомами, конечно, можно ожидать больших времен когерентности. Ну, есть, соответственно, атомная физика, которая много всего про них знает. То есть многие модели очень точно работают. Вот. Значит, но это преимущество одновременно является и трудностью, поскольку, значит, они не заряжены, с ними нельзя обращаться как с ионами. Вот. А можно делать, на самом деле, вещи, которые стали возможны, ну, где-то в конце прошлого столетия. Вот. За это были даны какие-то, значит, Нобелевские премии. Наверное, вы об этом тоже так же знаете, так сказать. Это создание, значит, оптических потенциалов при помощи лазерных лучей, создание потенциалов для атомов и маленьких частиц, не только для атомов. Но здесь речь идет о том, что можно делать оптические пинцеты, можно делать оптические решетки. Вот. И с точки зрения реализации квантовых вычислений, оптические решетки действительно являются очень такой интересной платформой, потому что здесь, значит, можно создавать периодический потенциал для нейтрально заряженных атомов. Вот. И потенциал может быть как одномерный, так и двумерный, даже трехмерный. Вот. И в этом потенциале важно, конечно, заставить, чтобы атомы взаимодействовали. Ну, значит, как делается такая решетка? Значит, вещь, в принципе, наверное, всем известная. Значит, мы берем 2 лазерных луча, направляем их друг на друга. Вот, при этом позаботимся о том, чтобы они имели одинаковую частоту и одинаковую фазу. То есть мы должны эти 2 лазера, значит, реализовать одинаковую фейз-лок. То есть мы должны захватить фазу, чтобы она не менялась. И дальше такие 2 волны, которые распространяются в противоположном направлении, они формируют стоячую волну. Вот. Значит, в этой стоячей волне будет иметься модуляция интенсивности электрического, ну, соответственно, магнитного поля тоже, с периодом в полдлины волны. То есть будут возникать стоячие волны, и у них будут, соответственно, пучности и узлы. Вот. С периодом полдлины волны лазерного излучения. Вот. Ну и дальше вот в этом самом, значит, поле стоячей волны будет на атомы действовать периодически, значит, переменное электрическое поле, создаваемое лазерным лучом. Вот. И в случае значительной интенсивности этого поля в атоме существует эффект, известный в атомной физике, это эффект Штарка, состоящий в том, что энергетические уровни, значит, начинают изменяться, а именно они отталкиваются при увеличении мощности лазерной накачки. Вот. Ну и дальше используется здесь тот факт, что если мы отстроим лазерный луч в голубую сторону, то есть возьмем длину волны немножко меньше, чем длина волны, соответствующая переходу в атоме, тогда атомы начинают притягиваться к точкам максимальной интенсивности электрического поля, то есть это получается, они будут располагаться в пучностях. А если мы отстроим в обратную сторону, сделаем, соответственно, длину волны немножко больше, чем длина волны перехода между состояниями, основным возбужденным выбранным нами атоме, то эти атомы будут притягиваться к точкам минимальной интенсивности. То есть, выбирая отстройку лазера, мы можем фактически менять взаимодействие атомов с стоячей этой волной. Ну и понятно, что если мы можем, значит, расположить эти атомы в локальных минимумах, создаваемых вот этим самым взаимодействием с лазерным излучением, то мы можем реализовать регулярную структуру из таких атомов. Вот. Вещь известная. Значит, теперь давайте подумаем, как же мы заставим атомы взаимодействовать. Ведь период оптической решетки определяется длиной волны лазера. Вот. И здесь мы на самом деле имеем фактически характерный масштаб, ну, наверное, что-то там, какая-то часть микрона. То есть, если в видимой области, это, в общем-то, там, в районе полмикрона. Ну, полдлины волны будет, соответственно, половина этого. Вот. Это довольно здоровое расстояние, то есть, это сотни нанометров. Вот. А атомы, как мы знаем, маленькие вот, в своем основном состоянии. Вот, они имеют размер порядка нескольких ангстрем. Вот, и взаимодействие между ними, естественно, очень мало, потому что они не имеют никакого электрического заряда, а могут только быть поляризованы. Вот, и для этого используется значит, специальное состояние атомов, которые можно также приготавливать при помощи лазерной накачки, а именно высоковозбужденное состояние с большим квантовым числом n. Такие состояния называются значит, ридбергскими. Вот. И в этом случае фактически атом возбуждается до энергии, которая очень близка к энергии его ионизации. Ну, понятно, что когда у нас значит, электрон находится совсем близко к ядру, то расстояние между уровнями довольно большое, но за вот этой известной формы потенциала взаимодействия электрона с ядром, кулоновского потенциала, расстояние между уровнями вблизи порога ионизации становится совсем маленьким. И в этом случае атом фактически становится большим, потому что фактически электрон находится довольно далеко от ядра. Вот. Ну, значит, радиус, в принципе, атома характерный, значит, электронного состояния в атоме пропорционален квадрату главного квантового числа. Вот. Если переходы между значит, состояниями с маленьким n, они находятся где-то в оптическом диапазоне, ну, это линия Лаймана, линия Балмара серии и так далее, вот, то переходы между соседними состояниями с очень большим числом n, они находятся в совсем другом диапазоне, не в электрон-вольтах по энергии, а в микроэлектрон-вольтах, что соответствует фотонам микроволнового диапазона. Вот, поэтому, если мы теперь возьмем и приготовим атом вот в таком высоко возбужденном состоянии, в ридбергском состоянии, то фактически его размер будет, ну, в общем, сравним с микроном, и фактически он будет иметь характерный размер, который порядка периода создаваемой нами оптической решетки. Вот, это очень здорово. Вот, значит, дальше, значит, что мы можем здесь сделать? Ну, они заряжены атомы нейтрально, но, тем не менее, они могут быть поляризованы, и поэтому между ними будет, вообще говоря, взаимодействие. То есть, на самом деле, дипольный момент атома пропорционален квадрату квантового числа n. Вот. А энергия взаимодействия, как нетрудно сообразить, между соседними атомами пропорциональны четвертой степени квантового числа. Вот, поэтому фактически, если мы захотим теперь сделать, ну, скажем, атом отдельно у нас является кубитом, мы выбираем в нем какие-то два состояния риддерских, называемых 0 и 1, и оптикой приготавливаем эти состояния, то мы можем, значит, используя вот это вот дипольное взаимодействие, иметь вполне значительную как бы величину расщепления между состояниями 0,1 и 1,0. То есть вот состояние в двухкубитной системе, если у нас есть один кубит 0,1, второй кубит тоже 0,1, то, значит, в системе двух взаимодействующих кубитов у нас есть 4 состояния: 0,0, 1,0, 0,1 и 1,1. Вот расщепление между 0,1 и 1,0 у нас будет иметь порядок характерный, связанный с этой энергией взаимодействия. Если ее разделить, значит, на постоянную планку, это дает примерно, значит, энергию фотонов, ну, или энергию, так сказать, характерную частоту порядка нескольких десятков мегагерц, что на самом деле очень здорово. Вот. И вообще говоря, так сказать, мы можем позволить себе тогда при помощи импульсов вот этого электромагнитного поля устраивать взаимодействие и устраивать вентили между соседними атомами. Вот, значит, ну, дальше давайте подумаем, значит, или посмотрим скорее даже на вот те достижения, которые в этой области сделаны. Значит, эта область очень быстро развивалась в последние, скажем так, десяток лет особенно. Вот, и здесь, значит, при помощи, ну, фактически процессоров, которые программируются для выполнения определенных целей. Значит, здесь, конечно, используется и машинное обучение, используется электроника на FPGA для того, чтобы делать это быстро. FPGA по-русски называется PLIS. Вот этот термин вы еще будете слышать в рассказах про другие кубиты. Значит, FPGA – это Field Programmable Gate Array. То есть это не микропроцессор, а это фактически электронная схема, которую можно программным образом, топологию которой можно программным образом модифицировать. И такие схемы сейчас используются во многих областях для того, чтобы делать очень быстрый анализ данных и, соответственно, управление сложными системами при измерении какого-то большого количества данных, которые фактически определяют алгоритм этого управления. Вот. Ну, что такое PLIS, я думаю, вы можете сами посмотреть, так сказать, в принципе, русский перевод вот этого сокращения Field Programmable Gate Array, FPGA. Вот. Так, при помощи таких устройств делать специальные программы, специальные программные инструменты для того, чтобы создавать необходимые решетки. Что нам нужно сделать? Ну, скажем, мы создали атомное облако где-то в вакууме. Вот. Дальше мы известными там методами охлаждения атомов, значит, достигли какой-то низкой температуры. После этого мы создаем оптическую решетку. Ну, конечно, когда мы ее создаем, из газа атомы попадают в эти минимумы энергии случайным образом. Вот. Но можно более-менее, так сказать, научиться подбирать так, чтобы вот риддерские атомы имели размер такой, что они бы занимали отдельный минимум оптической решетки. То есть добавление второго бы атома не приводило к его захвату, а просто из-за того, что находящийся в минимуме решетки первый атом уже как бы меняет форму потенциала. Вот. И поскольку атомы не могут сидеть, находиться на голове друг у друга, то есть у них между ними существует естественным образом тоже взаимодействие, вот, на малых расстояниях. Вот, значит, здесь получается, что мы можем фактически распределить атомы, ну, более-менее, так сказать, в минимумах решетки. А дальше у нас будут какие-то точки, которые будут вакансиями, ну, где-то возможно, что будут два атома. И вот этот беспорядок можно убрать, используя оптические пинцеты, контролируемые также FPGA, которые, ну, научаются сначала на каких-то простых конфигурациях делать эти манипуляции, а после этого уже программа включается и расставляет атомы в нужном порядке. И вот вы видите на этих иллюстрациях из одной из не столь давних статей, где показаны в качестве примера иллюстрации приготовленное распределение атомов вот таким вот искусственным образом в трехмерной оптической решетке. Вот, то есть это все можно делать, вот это все делает обучаемая электроника. Вот, и дальше, значит, наша с вами задача – это, ну, научиться как бы теперь с этими регулярно расположенными атомами в решетке работать. Вот. Значит, как устроен, в принципе, такой компьютер? Значит, у нас имеется высоковакуумная камера. Дальше у нас имеется, значит, в этой камере лазерные лучи, которые создают оптическую решетку. Эти же лазерные лучи мы можем, ну не эти же, а другие какие-то лазерные лучи мы можем использовать и должны использовать для приготовления каких-то состояний отдельных атомов. То есть мы можем их готовить в состояниях там 0 вот, или 1. Вот, ну, обычно, так сказать, нижний по энергии состояние называется нулем. Вот, и значит, путем накачки мы приготавливаем это состояние. Затем есть специальная, как бы, сложная электроника, включающая в себя компьютер FPGA, которая значит, управляет вот этими всеми лазерными лучами, пинцетами и так далее, которые должны расположить атомы в регулярном, значит, порядке. Вот. Мы должны, конечно, дальше заботиться еще о том, что нам более-менее непрерывно нужно, ну или, скажем, время от времени в перерывах между циклами работы квантового компьютера нужно эти атомы охлаждать. То есть здесь требуются, естественно, дополнительные какие-то усилия по охлаждению лазерному и другими методами. Вот. И затем, значит, есть устройство считывания состояний. Значит, атомы, когда они приготавливаются в состояниях 0 и 1, одно из этих состояний делается флуоресцентным. Вот, то есть при помощи накачки можно возбудить атом из состояния, скажем, 0, и тогда наблюдается излучение на другой длине волны, которое мы можем регистрировать при помощи камеры, CCD-камеры. Вот. А если атом находился в момент прикладывания, значит, накачки в состоянии 1, то этого излучения не возникает. Таким образом, у нас как бы есть возможность эти атомы видеть глазами, если они находятся, ну, в определенном, как бы, известном нам состоянии. То есть мы можем фактически за счет флуоресценции считывать информацию о том состоянии, в каком находится каждый отдельный атом. Но что нам теперь нужно? Конечно, нам нужно учиться делать, значит, отдельные индивидуальные вентили между, значит, ну, на отдельных атомах. Вот. И нам нужно научиться делать взаимодействие между атомами, соседями или ближайшими соседями или какими-то более удаленными соседями для того, чтобы выполнять квантовые вычисления. Вот. Ну, вот здесь слайд, который я привел, это слайд, значит, который взят из презентации компании Cold Quanta. От компаний, которые занимаются атомами, несколько, но вот очень, как бы, известная, значит, компания в этом, значит, в этой области, это та, которая была создана Михаилом Лукиным в Гарварде и MIT, то есть это в Бостоне такая компания существует, и, в общем, довольно быстро они продвигаются в сторону построения масштабируемого квантового процесса. Значит, это вот одна из альтернативных, как бы, картинок того же самого. Вы видите здесь, значит, компания Pascual, французская, которая занимается именно этой технологией. Значит, они здесь нарисовали это немножко по-другому, но, в принципе, в общем, все тоже очень похоже. То есть есть лазерная какая-то лаборатория, где происходит охлаждение и захват атома в ловушке. Дальше есть управление всякое при помощи разнообразной электроники. Вот, построение квантового регистра при помощи этой электроники. И дальше постоянно работает электроника, которая управляет лазерами, использующимися для возбуждения атома в нужное состояние, для накачки. Электроника, которая управляет, значит, микроволновым или, значит, более низкими частотами, которые связывают рейдерские состояния. Вот. Ну и дальше, соответственно, есть классический компьютер, который всем этим управляет. То есть довольно такая сложная штука, но сам квантовый регистр, вот вы видите его, здесь он нарисован, здесь вот внизу справа. Это фактически упорядоченные атомы в высоком вакууме, которые создаются при помощи вот такой вот техники. Вот. Ну, как можно перепутывать атомы? Значит, есть вот ну, такая наиболее продвинутая технология, которая была разработана в Гарварде. Значит, это так называемая ридбергская блокада. Она состоит в том, что если определенный атом ридбергский переходит в возбужденное состояние, то у него меняется дипольный момент. И это значит, приводит к тому, что взаимодействие этого атома к соседним атомам фактически смещает уровни энергии в соседнем атоме. Таким образом, поле, которое было бы резонансным для уединенного атома, становится нерезонансным для атома, находящегося вблизи возбужденного. И дальше, меняя, собственно, величину вот этой вот рейдерской блокады, меняя частоты и отстройку, можно фактически изменять радиус взаимодействия вот определенно выбранного в решетке атома со своими соседями. Вот. Но это, значит, такой способ, который, мне даже, по-моему, слайда здесь нет на эту тему. Более иллюстративный способ показан вот на этой картинке, который взят из другой статьи, где в качестве метода создания вот таких вот двухкубитных вентилей предлагается использование значит, ну, либо третьего лазера, который имеет, кроме двух, которые создают решетку в противоположном направлении, противоположно направленными пучками, можно наложить как бы на эту решетку еще длину волны, которая будет в 2 раза больше, и тогда создать такую двухпериодичную решетку, то есть периодом в 2 раза длиннее. Вот. Ну, либо можно играть с сдвигом фаз между двумя лазерами, которые сбиваются вот в области, где возникает такая решетка. Ну и дальше можно, соответственно, меняя величину этого сдвига фаз и меняя интенсивность третьего лазера, можно менять форму потенциала. Вот. Если взять 2 соседних как бы места в решетке, то можно фактически барьер между этими местами сначала уменьшить, а после этого увеличить. Таким образом, мы можем приготовить сначала, значит, 2 атома в состоянии в одноямном потенциале, как показано здесь, а потом, значит, изменив фазу лазерного излучения, можем разнести эти атомы в пространстве, как показано справа. И таким образом можно фактически создавать ну, в какой-то степени похожую манипуляцию на ту, о которой мы говорили, как раз разбирали с вами двухъямный потенциал. В данном случае мы говорим о реальных физических атомах, которые находятся в этом пространственном потенциале. Вот, они имеют определенную структуру уровней, как система двух связанных атомов. Этой структурой можно управлять. Значит, если у нас имеется низкий барьер между двумя ямами, то существует, соответственно, туннелирование атомов. Они могут меняться местами, и это, значит, процесс называется super exchange. То есть они одновременно перепрыгивают, один перепрыгивает направо, другой перепрыгивает налево. И, соответственно, 2 таких состояния, up-down и down-up спины, они могут, они, естественно, возникает определенное, снимается вырождение за счет туннелирования, и возникает расщепление, на частоте которого можно подавать управляющие воздействия электромагнитными импульсами. Вот. Ну, детали мы здесь, конечно, совсем с вами разбирать не будем. Значит, по отношению к атому мне хотелось бы вот что сказать. Значит, вот атомная платформа долгое время, ну, до последних таких вот событий, которые уже привели к появлению масштабируемых процессоров, но до последнего времени они рассматривались такой идеальной, ну, как бы, реализации так называемых квантовых симуляторов. Вот я про это хотел немножко поговорить. Значит, вот мы с вами говорили о том, что вот существует как бы концепция квантовых компьютеров, где мы можем выполнять, вообще говоря, произвольный алгоритм, имея в распоряжении однокубитные и двухкубитные операции. Вот. Но, значит, на самом деле здесь, как бы, конечно, просто разбивается наша задача на какие-то элементарные участки, которые имеют стандартные названия. При этом не факт, что мы можем прийти там, из точки А в точку Б, Гильбертово пространство там, 2 в степени n, размерностью 2 в степени n для n кубитов, мы можем прийти максимально эффективным образом. То есть мы пойдем каким-то путем, который нам позволяет, значит, вот, выбранный нами алгоритм. И этот путь может быть по времени долгим. Это означает, что мы можем значит, нам потребуются довольно долгие манипуляции, а за это время система может стать дикогерентной, и, в общем-то, мы никакого результата не получим, потому что у нас количество ошибок, которые накопятся, будет очень большим. Другой подход для определенного класса задач, он называется, значит, не квантовый компьютер, а квантовый симулятор. Вот. И здесь речь идет немножко как бы о более общей задаче. То есть мы создаем какую-то систему с каким-то взаимодействием, которое описывается каким-то гамильтонианом. Вот. И дальше мы прикладываем определенное воздействие на этот гамильтониан, и система меняет свое как бы состояние При этом это состояние может меняться как динамически, так и адиабатически. Вот адиабатические квантовые компьютеры – это то, что делала компания D-Wave и что делают на других платформах тоже. Здесь фактически речь идет о том, что у нас приготавливается основное состояние выбранного нами гамильтониана. Вот, и дальше это состояние медленно меняется во времени, под воздействием параметров, которые мы можем менять в данной системе. Вот. Ну, если существует какой-то мэппинг этого гамильтониана на полезную задачу, ну, скажем, задачу оптимизации, то можно фактически, прочитав конечное состояние, основное состояние этой системы за счет адиабатических манипуляций, получить какой-то интересный ответ. Это, значит, вот принцип работы квантовых так называемых аннилеров или квантовых адиабатических устройств. Ну, аннилер немножко другое, но хорошо, это квантовые адиабатические вычисления. Вот. А квантовый симулятор включает в себя более общую какую-то такую группу устройств, которые фактически выполняют зависящие от времени манипуляции с многокубитной системой. Ну и здесь понятно, если мы можем одновременно воздействовать на разные кубиты, то есть не просто там на 1 или там на 2 кубита, выполняя одно- и двухкубитные гейты, а воздействовать на все сразу, то мы можем, ну, скажем, из точки А пространства Гильберта в точку Б пространство Гильберта дойти гораздо более коротким, быстрым путем. Вот. Но, естественно, этот путь будет зависеть очень сильным образом от вида того гамильтониана, который описывает систему. Вот. Но сейчас, на самом деле, развивается очень бурно тоже технология, которая называется многокубитные вентили, multi-qubit gates. Вот. И здесь, конечно, очень много еще предстоит сделать и много всего интересного. Кстати, я заметил, что я говорю по-русски. Наверное, я поступаю неправильно. Да, прошу меня извинить, наверное, нужно перейти на английский. Ну, как-то я вот не успел переключиться. Не обижайтесь. Перехожу на английский. Ладно. So, this slide shows a comparison. Да-да.
А мы тут решили нашей маленькой группой, что может стоит все-таки говорить по-русски, если вы не против сами.
Ну, если это общее мнение, вот Настя мне
написала. На самом деле, да, мы вообще все не против, и из МИСИСа тоже студенты. Вот.
Я бы
это всяко понятно.
Английский скорее.
Есть кто-то, кто против того, чтобы говорить по-русски?
Ну, я бы послушал на английском с большим удовольствием.
Ну, вот видите, значит, тогда вот в международной аудитории, например, вот я учу студентов в Германии и люблю читать лекции по-английски. По-немецки я читаю хуже, но тоже умею. Вот. Но если вот я спрашиваю, на каком языке будем читать, и хотя бы один человек в аудитории говорит, что вот давайте по-немецки, мне приходится читать по-немецки. Мне кажется, вот в этой ситуации я должен поступить все-таки так же. Вот. Поскольку вашей учебной частью заведует Настя Горяйнова, и я ее напрямую спросил, она сказала, что читать по-английски. Вот. Поэтому, наверное, все-таки давайте, ребят, буду читать по-английски, а вопросы можно задавать по-русски. Вот. Ну, экзамен, соответственно, тоже можно по желанию сдавать по-русски или по-английски. Давайте так. Хорошо?
Хорошо, а вот вопрос, а все эти записи, которые вы делаете, занятий, где их потом можно найти? Можно ли потом их найти?
Ну, конечно, но Настя где-то их выкладывает, и слайды, соответственно, я тоже ей предоставляю. Она мне обещала прислать ссылку, но пока не прислала, куда выложить. Вот, то есть все это можно будет
Хорошо, спасибо.
посмотреть. Как бы просто это время, и, наверное, слушать, как говорится, так или иначе, наверное, правильно вживую, потому что вы можете вопросы задавать. Okay, so let us switch to English. You are welcome to ask me questions in Russian. I will enjoy answering them in Russian, but let us talk English further down this lecture today. Okay, so this slide, actually I borrowed from the head of FIAN, Nikolai Kolachevsky. which is actually probably like 2 or 3 years old, this slide. But it reflects the comparison between trapped ions, neutral atoms, and superconductors. So we talked about trapped ions already. We briefly talked now about neutral atoms, and we are going to talk about superconductors in the lectures, which will be later, starting from 2 weeks from now. So the criteria of comparison are related to scalability, are related to DiVincenzo criteria. This criteria we were discussing in the first lecture. And one of the criteria is a scalable technology. So the scalable means that it's русское слово здесь масштабируемая технология. So scalable technology means that we can basically increase the number of participating qubits in the system, and the control of the qubits, of course, it will not necessarily will be preserved exactly as it was for 1 qubit, but it still should be feasible to make manipulations on multiple qubits in a similar fashion. And with trapped ions, the typical number of ions is in the range of several tens. Now, with ions, there are also simulators which simulate different Hamiltonians. In this case, you don't need all sophisticated control of qubits, and the number of ions in the chain, to my knowledge, went up to 100. But if you go really to this number, then of course the number of vibrational modes in the lattice also increases, and cooling all them down becomes really rather complicated. So you get this large overhead of increasing the number of modes. In computing architectures, the number of qubits was comparable, several tens, and this number is growing now, looking into the development of the integrated technology using on-chip traps. Now, the coherence times with ions is about 60 minutes. This is really huge time, much longer than anything else you could see, maybe except for nuclear spins and solids at low temperature. The complexity of neutral atoms has been growing comparably. Also, people can have up to 50 plus qubits. And with superconductors, this number, actually 72 is not correct. The 72 processor of Google never worked. But currently, also in China, there are demonstrations of algorithms on processors of over 60 qubits. And IBM Quantum announced also the generation of over 100 qubits processors using superconducting qubits. Now, the next benchmark is comparing the coherence time, and here, as you see, ions are leading. Neutral atoms are somewhere in the middle, so this could be seconds or few seconds or fractions of seconds, while for superconductors, typically a fraction or order of 1 millisecond, which doesn't sound great. However, one should compare here not just the number of the quantity in time, but also primarily the ratio of the coherence time to the gate time. And this basically tells you how many operations can you do on the quantum computer before it gets decoherent, before the errors appear. And the superconductors have this ratio of the order of 10 to 4, while neutral atoms are doing better and ions are doing even better. And also this is reflected in the fidelity, which is basically the probability of not having the error. And for ions, both for single qubit and 2 qubit operations, you basically have not more than 1 error in 1,000 operations. While for neutral atoms is a little less, especially for the 2 qubit gates, and for superconductors is currently approaching also comparable numbers. Actually, superconductors 2 qubit gates are a bit better, but still not really beating the fidelity of ion gates. So basically, there's 3 leading platforms. The fourth platform, which we also talk about today, which are photons, is not on the stable because it's not the universal quantum computer, which can be built using photons. So we'll come back to this table when we discuss superconductors and see how much one can actually improve each platform. But both, all the 3 platforms are being now chosen by different startups and companies, and there are big players, including big industrial giants as Google and IBM and Microsoft, but also many smaller companies which appeared in very recent years. All right, so here is the summary about the 2 leading platforms of the table. The trapped ions have really long coherence times. They can be manipulated by microwaves and optical pulses. And they are forming a one of the leading platforms for quantum computers. Neutral ions are really most favorite platform for quantum simulations because one can really form regular lattices and nicely form model lattice Hamiltonians, which are interesting for a variety of materials problems, for condensed matter physics and beyond. They are operating using Rydberg states, highly excited states of atoms, which interact via dipole interactions. And one can change the interaction range, which is advantage over, for example, superconducting qubits. With ions, you could have the infinitely long range of interactions. So that's what we discussed on the lecture a week ago, that you could basically make interact any arbitrary ions in the chain, not necessarily nearest neighbors. Superconducting qubits mostly interact with nearest neighbors, and with neutral atoms, you could sort of choose this by making the interaction with nearest neighbors or next after next or even next after the next. So the interaction range can be changed by using Rydberg blockade. All right. Any questions about ions, atoms? It was, of course, very superficial, and I wouldn't really have chance in this very short introduction to go into details. But if you have quick questions, I would be happy to comment. Welcome also questions in Russian. Yes?
А зачем вообще используют сверхпроводниковые гейты, если там количество операций все равно не такое большое, и время когерентности не очень большое, и в целом они как бы уступают ионным или на нейтральных атомах?
Мы об этом будем еще говорить. Значит, здесь основная причина то, что сверхпроводниковые схемы делаются по обычной технологии, которая нам привычна из обычных компьютеров, только используют не полупроводники, а сверхпроводники. Имеется огромный простор в топологии схем, в средствах контроля и так далее. Вот. И на самом деле, конечно, это был очень неочевидный вопрос, если говорить, скажем, с ионщиками или атомщиками, которые делают свои версии. Каждый из них убежден, что их платформа лучше. Но глядя на то, что происходит, пока наиболее убедительные сильные результаты были достигнуты именно сверхпроводниками. Насколько это лидерство сохранится или изменится, ну, покажут ближайшие годы.
Спасибо.
Не за что. Ну, хорошо, если нет вопросов дальше, давайте двигаться. Okay, now we start with the next topic. Actually, I just catched up here with the previous lecture, which took me 40 minutes. Sorry about that. But actually, I should stop. I should remember now. I should stop at. Let me remember it. I should do it at 10 to 12, right? Is that correct? Or 20 to 12? Hey, are you there? Okay, I see the chat. Okay, 10 to 12. Thank you. All right, so we're talking the following about photons as qubits. Again, superficial, just as an introduction into this different platform, which we have as competitors. So Photons are very nice. They're excellent quantum particles. A lot of quantum physics has been learned from photons. They are quanta of light. They can propagate over large distances. They don't have mass. They don't have charge. So they weakly interact with the environment, and therefore they're very coherent. And in order to make a quantum computer, we should find basically encoding of states 0 and 1, and then make sure that we could make manipulation of the states. For example, we need to make a gate, make 0, 1, or make superposition of the two. And this has been done with photons in two different ways. The first way is choosing encoding in polarization. So in this case, you could polarize a photon in horizontal way, make horizontal polarization state 0, and make a vertical polarization state 1. In this case, one can rotate the polarization plane by using various techniques. We'll talk about them briefly in the following slides, and then make single qubit gates. And one can represent very nicely also polarization encoding into the Poincare sphere, which is somewhat similar to Bloch sphere. So basically, we'll have up will be horizontal polarization, down will be vertical polarization, and then by applying different rotations on the polarization plane, we'll be able to implement rotations over the sphere, similarly how we do it on the Bloch sphere. Now, another way of encoding, which in some sense is it's simpler to realize, because it's not always easy to rotate the polarization plane, is the so-called dual rail encoding, where the states 0 and 1 are encoded at the path, at the trajectory, or at the way the photon choose. Suppose we have an interferometer, which is shown here at the bottom here. We have a single photon source, and then a single photon, which is sent to interferometer, can have probability of 50% being transmitted through a beam splitter, which is a semi-transparent mirror, and 50% probability of being reflected. And then by using two more mirrors and another beam splitter, we can observe the interference of the photons in this interferometer. Now, actually, Nobel Prize of this year was given to famous physicists Alan Aspect and Anton Zeilinger for the experiments which actually were done with photons, showing the entanglement, which is actually was using a similar technique to demonstrate distant entanglement between photons by measurements. Here, basically, we know, and this has been done already a long time ago, that if we send a single photon in this interferometer, single photon also choose one way or the other, and there is an interference between those ways. We could really observe for a single photon full interference as we observe for continuous waves. And that's really remarkable that the photon will go one way or the other. We will not know which one until we measure. And by doing the measurement, we project, of course, the state to the classical states. And we can choose the rotation of states 0 and 1 by putting here small plates of particular thickness, where the velocity of light is reduced, and therefore, depending on the thickness of the plate, one would have different phase for the propagating path. And then by using here a single photon detectors, which will click once the photon arrives there, we would be able to observe the interference such that the interference in the horizontal one will be proportional to the cosine square of the difference between the phases of the two phase shifters, and the upper one will be the sine square of the phases of the two phase shifters. By the way, the single photon detectors are nowadays are made of superconductors, and there is a outstanding group in Russia led by Grigory Goldsman, who is also one of the group leaders in the Russian Quantum Center. And he and his group actually developed over many years superconducting nanowire detectors, which are being used around the world to detect single photons in the visible range and also in the telecom communication range of 1.5 micron. That's where actually most of the photonic circuits work. Now, the beam splitter, where we split the incoming photon into the two paths, is nothing else as the Hadamard gate, where we basically form a superposition between 0 and 1, because the transmission and reflection have the same probability. And the phase gate, as I already explained, is a thin plate with particular thickness, which will rotate the phase of the propagating photon here. Now, when we deal with polarization, you should remember, of course, from optics that there is a phenomenon called birefringence. In German, this is doppelbrechend. In Russian, is двойное лучепреломление. And if you take calcite crystal, which is плавиковый шпат, then you would have the two different propagation speed, two different refraction index along the direction which is along the optical axis and the horizontal axis, and there will be basically parallel polarization, which will be propagating on one axis, particular polarization propagating on the other. So using this this type of plates, this physics, one can make the so-called lambda half plate, which rotates polarization by pi by changing the projection of the horizontal polarization and not changing the vertical polarization. And this will form the superposition between horizontal and vertical polarization if this particular plate has particular thickness. So this is an example of implementing NOT gate for encoding in polarization states. One can also make the conversion between two different types of encoding. This is also very, very important and interesting. So one can use the so-called polarization beam splitter, which are two glued together pieces of glass. In this case, the initial polarization encoded state, which will be alpha H plus beta V, where alpha and beta are the complex coefficients reflecting the share of each eigenstate in the incoming arbitrary state, will then be separated in H and B. And then by changing the path, for example, by putting here the phase shifting plates on the horizontal place, on horizontal branch and vertical branch, and horizontal branch, upper horizontal branch and lower horizontal branch, we'll be able to manipulate the H polarization and V as dual array. And then by placing at the end another polarization beam splitter, one would be able basically to convert back into the polarization encoded light. Of course, after doing some, for example, processing with phase shifting and so forth of the dual rail encoding. So this is convenient if one really wants to use both polarizations in one setup. What is very difficult with photons and maybe almost impossible are 2-qubit gates. And that's why photons are not being considered as leading platforms for quantum computing. They could be used for quantum computing, but in different sense. And the reason is that we need to make photons interact. So 2-qubit gate means that we need to make an interaction between two qubits, either polarization encoded or dual rail encoded. And in this case, this is really, really difficult. So the only standard way of making interaction of free propagating photons is using the Kerr effect. So Kerr effect is a nonlinearity which occurs in various crystals where the electric field can change the refraction index of the crystal. Now suppose that you have a photon propagating in a crystal, and this photon generates electric field, local electric field in particular location of the crystal. So this field obviously is very tiny, very small of a single photon. And the interaction between photons can be achieved here by the fact that the second photon, which will propagate nearby, will notice the electric field of the first photon and will experience a small delay due to the varied refraction coefficient at the local position of the first photon. So this is a very simple intuitive explanation, what is basically the Kerr nonlinearity, but you can already guess that the nonlinearity from a single photon will be really tiny. And in fact, this Kerr effect for optical photons is extremely weak. This is the phase shift in the single photon regime is as tiny as 10 to minus 18. And also the Kerr medium is also absorptive and diffusive. So basically light is often getting scattered. So there have been many attempts to find more efficient ways of making photons interact, for example, using nonlinear elements as quantum dots. But sending two photons in a single quantum dot, it's possible, but it doesn't really look very scalable until now. So therefore, really the 2-qubit gates with photons still remain an unsolved problem, and photonic quantum computers, they function in different way. So the solution for photonic quantum computers was proposed in a paper a long time ago, more than 20 years ago, by Knigel, Lam, and Milburn, where they put forward the idea of using linear optics for that. And linear optics here means that if you, for example, have propagating photons in a particular setting, and then you measure the photon with a single detection, by doing the measurements, you also entangle photons which have been emitted, for example, in the entangled states. So if you produce entangled photons initially from your source, by measuring, you can basically generate additional entanglement by measurement. And this manipulation of the entanglement by measurement is in a way similar to using the 2-qubit gates, but they're not fully equivalent. So basically 2-qubit gates are realized without nonlinear elements, just by doing the measurement. But to do this, you need a source of entangled photons. So you need a source where you would know that there will be simultaneously coming out photons which will be automatically entangled. And the source for these photons, for such photons, has been proposed many years ago, I think over 20 years ago, maybe 30 years ago, and actually Anton Zeilinger, who got the Nobel Prize this year, one of three, he has been working on this for a long time. So this is so-called parametric down conversion. So if you take nonlinear optical crystal, for example, beta barium borate, then you could send the UV light, basically a high frequency photon or flux of high frequency photons. It has to be intense light. And then it down converts the UV photon into two photons of the frequency, which is exactly half of the frequency of the UV photon, incoming photon. And then one of these photons will have horizontal polarization, the other one will have vertical polarization. The illustration below shows the beam passing through this kind of crystal, where you see that the crossing point of the circles, if I'm not mistaken, here and there are photons which will be entangled. The problem here is that you don't know the polarization of these pairs of photons. They can be arbitrary, and therefore to measure the photon, which is if you measure the photon horizontally polarized, you already destroy the entanglement, and you also know the state of the other photon, which is produced in the same procedure. So this is the whole field for itself, and this field leads to building so-called photon sampling technique, which is the way of processing quantum information in a different way than universal quantum computers, which we mostly talk about. Unfortunately, we'll not have time and also no own expertise to cover the topic in this short introduction. But as introduction, the summary which I want to give is that there are also photonic companies working in this field. There is a lot of interest into the integrated optics, where you make photons propagate over optical waveguides on chip. And here you see an example. One can generate, for example, a squeezed light states using this little ring resonators. So the photon propagating in this transmission line in this waveguide actually splits fraction of it, so to say, into the circular resonator, and by that one generates non-classical states of light, which will be strongly squeezed. One can also use some gates for phase shifting. This is the way that basically you apply local electric field, and then you change the refraction index of the material of the waveguide, basically delaying the propagation of the photon. And then this kind of beam splitter or interference sections will be then influenced and the photons propagating in this multiple lines will interfere, and this interference can be controlled by these electronic means. But still, 2 qubit gates in full scale are not possible here, but the Knidler-Flamm Milborn architecture is possible to realize. And for certain applications, photonic chips may really have a big future. So problems here arise largely also in the interconnects. So there's a big topic how to bring the photons on chip without losing them. And people now use 3D nanoprinting using the 3D laser lithography, actually developed here in Karlsruhe in my neighbor, Martin Wegener. So this is basically bringing these large optical tables, which are typically used for photonic labs, on chip, and then doing all the manipulation with photons on chip. So this is a whole field for itself. So if you hear something about photonic quantum computer, just remember it's not universal quantum computer, it's something else which can be useful for something else. And I'm sure you'll hear about that, or maybe heard already about that from other courses in your quantum technologies curriculum. All right, any questions to photons? Okay, let's move on. This was really superficial step in. Let's go deeper into the solid state technologies. Let's start with talking about impurities. Well, using the semiconductor technology is very attractive. And as you know, this technology has been developing over more than say 70 years, and there is this Moore's law which shows that it's still progressing. One can really make very tiny structures, and those structures will have only few electrons very soon, or maybe already have. So can one really use this technology for quantum computing? And this has been, of course, very relevant question, which was attempted to be answered by many people. But still, while transistors themselves, they operate using quantum mechanics, based on principles of quantum mechanics, their band structure is explained by that. But having control over individual quantum states in transistors in semiconductor devices, until now was looking very, very difficult. But how about using this technology really to make some manipulation of individual quantum systems? And this question was actually put forward by Kane in his famous paper. This was a theory paper, or basically proposal made by Kane, which was published more than 20 years ago in Nature. And as you may know, one of the typical doping materials which is used to add or remove electrons, in this case, add electrons to silicon, basically make silicon N-type, is the phosphorus. So if you put the phosphorus atom in silicon lattice, then phosphorus will be different from the rest of the lattice by the fact that it will have spin 1/2, because phosphorus has odd number of nucleons. And typical silicon, I would say 99% of atoms of silicon in natural silicon are silicon 28, which are spin-free. So they don't have any own spin. And they are also good isolators at low temperatures, because silicon has a gap of the order of electron volt. And if you cool this material to very low temperature, it becomes really excellent isolator. So now suppose that we consider a single phosphorus atom inside silicon, and we are looking into this spin of phosphorus. Now, phosphorus can take electron or not take electron. This is a question if we catch or not catch an electron on this impurity side. However, the spin of nuclei is always there. And if you apply a magnetic field, then there will be splitting between the energy levels of the spin. There will be Zeeman splitting, of course, with the magneton of the nuclei, 3 orders of magnitude smaller than Bohr magneton. However, this nuclear spin of silicon is located in this spin-free space, and it very weakly interacts with environment. So basically, the coherence times which have been measured on silicon doped by phosphorus atoms, one can distinguish, of course, the particular frequency of the transition between the spin states of phosphorus 31 by using nuclear magnetic resonance. So the coherence times which were measured were actually reaching hours at low temperatures, and even at high temperature, at room temperature, they are really in the range of minutes and more. And the T2 time, which is associated with the dephasing, basically, if the energy levels of the two spin states are fluctuating, then the phase of the superposition state prepared between the two ground state and excited state of the spin will be dephased, and these times are, of course, significantly shorter. These times will be also influenced by the impurity spins of, for example, other types of isotope of silicon, which will not be spin-free, or will be influenced by any other external fields. So this is really attractive that one can use these individual spins of phosphorus even at room temperature. But now a big question which Kane actually proposed to answer in his theoretical paper was how to manipulate and how to read out these nuclear spins. First part of this. And if you want to build a quantum computer, you also need to find a way how to couple these individual nuclear spins. And the idea was as follows. So typically, phosphorus atom will catch an electron from the crystal. So the electron will have lower energy there. It will be sitting in a gap, in a particular energy level, in the forbidden gap, but close to the conduction band. And the coupling of the electron to a donor is actually very weak. So it's in the range of tens of milli-electron volts. So again, the gap is in the range of electron volts, so it's really orders of magnitude smaller. This very weak coupling means that the electron state is going to be delocalized around phosphorus atom. And if an electron is located at the phosphorus atom, its spin will interact with the nuclear spin of the phosphorus. So this effect is called hyperfine splitting, which you know from atoms. And this is exactly the phenomenon which can be used for using the control of the nuclear spin via the electron state. So the Hamiltonian of this interaction between nucleus and electron can be written in this form below. So here you have the electron Hamiltonian, where you have the Bohr magneton times the magnetic field times the spin operator, then the electron spin operator, then the nuclear energy is going to be proportional to the nuclear magneton, and the interaction energy, which is this hyperfine energy of interaction, is characterized by the product of the two spin operators, and the constant of interaction is a product of the nuclear spin and the electron, nuclear magneton and electromagneton. So this is the hyperfine interaction, which is of course well known. But then now let's think how we can make the states interact. If we now form two phosphorus atoms at a distance near each other, which means at a distance of, let's say, a few angstroms, or maybe a few tenths of angstroms, the interaction between them will exist, but it will exponentially decay with increasing the distance between them. So this is the calculation which has been done in that paper. This is the interaction energy measured in frequency. Basically, to get the energy, you need to multiply this scale by Planck's constant. It's here in hertz. So somewhere here is in gigahertz, somewhere here is megahertz. And you see that the interaction energy at a distance of about 200 angstroms is going to be in the range of gigahertz, while if you increase the distance to, let's say, 400 angstroms, it's going to drop down by 3 orders of magnitude. So this is, of course, all theoretical, and it's quite kind of evident that this interaction is difficult to control experimentally, because you need to put really the two phosphorus atoms nearby, and you also need to locate electrons on both atoms, and need to be able to somehow control that. And another disadvantage of that is that in this case, the coupling between the two states is always fixed, it's always on. So if you put physically two phosphorus atoms at a distance of, let's say, 200 angstroms, then this interaction is always fixed, so you cannot do much. However, one can actually use here a trick, and this trick is possible due to the fact that one can actually use the electric field control of the extended electron states around phosphorus atoms. As I mentioned, this electron state is extended over 100 angstroms or so, and actually even more. And therefore, one can use if one can manage to put phosphorus atoms slightly below the surface of silicon, one can use the metallic electrodes on the surface of silicon to change the shape of electron electron orbital around the phosphorus nucleus. And basically, by doing that, one can distort the electron cloud and introduce manipulation of the single qubit state. Of course, we have to remember that we manipulate only electron, and electron is connected to nuclear spin via a hyperfine interaction. So actually, we have to sort of do it in two steps. We have to apply the pulses which will be resonant with the hyperfine splitting, and then we also have to apply the gates which will modify the electron states and consequently also the nuclear state via hyperfine splitting. Moreover, one can make the wave functions of two electrons located at two different phosphorus atoms overlap in situ if one use the G gate, or this kind of middle gate on chip. So if one, for example, applies positive charge here, then the two electron states are sort of attracted. They're negatively charged. They will attracted to this gate, and then they will overlap. And of course, if we consider now electron being here and electron being there will be states like 0, 1 and 1, 0. So there will be swap oscillations. For example, if one prepares here an electron, a single electron for the two phosphorus atoms, then this electron will perform swap oscillations between the two sides, and therefore will entangle two nuclear spins. This really looks like making a really complicated staircase, which is very fragile and very sophisticated. But surprisingly, actually, it's not impossible. Now, the last question which we still need to answer before looking at the possible realizations is the way how we are going to read out this thing. Suppose we learn to manipulate the electron states, individuals from the phosphorus nuclei states via hyperfine interaction, and also can entangle nearby located phosphorus atoms. But how can we read this thing? And reading can be done with a device which is called a single electron transistor. Now I want to ask you a question. So do you all know what is single electron transistor, or should I explain it to you?
Explain, please.
Good, because I always do it in my solid physics course. But okay, nevertheless, it's good to remind. Now, what is single electron transistor? It's a device which has, as any transistor, it has source and drain, right? And something in the middle. So it has 3 electrodes. And basically, this is shown here in the schematics on the right. So S is source, D is drain, and Q is the small metallic grain which is coupled to 2 electrodes. Now, if you take the capacitance, if you take this middle green island to be very small, its capacitance to the environment is going to be very tiny. Now you should remember that the energy of the capacitor, which you need to charge the capacitor, is proportional to square of the charge divided by capacitance. So the smallest charge which you can bring from source to drain by tunneling through this very thin gray tunnel barriers is the electron charge. Suppose at this green grain you have 1 million of electrons, and this grain has a very small capacitance. If you want to increase the number of electrons on this grain by 1 to make it 1,000,001, you need to for electron to tunnel from source into this island and then eventually tunnel away from drain. And this electron tunneling to this little tiny grain in the middle has to overcome the Coulomb energy. So if the voltage you apply is smaller than the so-called Coulomb blockade voltage, which is sufficient for the electron to tunnel, which is sufficient to overcome this energy. The energy is just voltage times the electron charge, right? So then the electron is tunneling. If the voltage you apply is smaller than this Coulomb blockade voltage, then there is no tunneling. So basically, this device will show no current until the voltage applied is larger than the voltage of the Coulomb blockade, which is square of the electron charge divided by the capacitance of the island. So basically, after some voltage, there will be increase of current because electrons will start tunneling through the transistor. And then once you have increased the electron to 1,000,001, there will be again another blockade, because if you want to increase the charge on the island yet by 1 more to 1,000,002, then there will be again blockade voltage. So there will be basically, if you apply increase the voltage between source and drain, there will be sometimes current appearing, sometimes there is no current. So it will be like a periodic increase of the current as a function of the source drain voltage. Now, this thing is a transistor because the onset of this current you can control by the gate which you apply to the middle island. So basically, if you apply here a particular gate, then you could change the voltage at which the current sets in, simply because you polarize the charges on this little grain. So basically, you can fabricate this kind of device using metallic electrodes. Typically, people use aluminum and then use electron beam lithography to form an island of the size of, let's say, a few tenths of nanometer in size. And this few tenths of nanometer island will have capacitance which will be in the range of fraction of femtofarad, and actually will be some couple of attofarads. And this kind of capacitance is already sufficient to create appreciable Coulomb blockade, which will be seen in this device at low temperatures in the absence of large thermal fluctuations. So, and then basically, if what is not shown on this picture on the left is the gate, but suppose the gate is somewhere here on the side. So this is source, this is this drain, this is a small island. Okay, and then here from another side, from the bottom of the substrate, you have a phosphorus atom sitting only a few nanometers away from the interface. How to do it, I will tell you a little later. And then these phosphorus atoms may catch electron or may not catch electron. This electron basically will form, will induce some electric field on the island, so it will be basically modifying the potential of this middle grain. In a similar way as does the gate, it will influence the onset of the Coulomb blockade. So basically, the electron can be trapped on this phosphorus atom. Its presence will influence the onset of the Coulomb blockade of the single electron transistor, and the source and drain current will depend on the presence or absence of the electron on the atom. So this is the one of the first experiments which was made in Australia. And actually, when the whole hype of quantum computers started about 20 years ago, came proposal, as you have seen, paper was 98. It was already there. And Australians were the only country which really invested very heavily in silicon impurity platform for building quantum computers. They had the whole huge collaboration working on the way to embed phosphorus atoms into silicon and then trying to measure them. I noticed the time is now for the break, so I think it's a good time to make a break. I will tell you how they actually did it and tell you about the most recent news from this technology, which are pretty amazing and actually are only like a few months old. So let's have a break, 10 minutes, and we see us at 12. Prepare your questions or ask questions now if you want. Okay, no urgent questions, then let's make a break and then we meet in 10 minutes. Ой. Okay, so let us continue. Давайте продолжим. So this is the device which was fabricated in the lab of Andrea Marello in Australia back more than 10 years ago, which actually made it possible to perform really unique experiment. As you see, these people have been working on Keynes' proposal for more than 10 years. So what they've done, they covered the silicon chip by protection layer, and then irradiated with the whole sample with high energy phosphorus ions. And in this dashed line, you see this, my mouse is not working at the moment. In this dashed rectangle, they had a small opening of about 90 times 90 nanometer. And according to the flux of phosphorus, they were expecting there to have about 3 phosphorus ions in the small area. In the rest of the circuit, there was no phosphorus ions implanted. And then on top of that, they formed a device which has here a source. This is a source. Now mouse is working. This is a drain. And this is the middle electrode. And these are the two gates which were used to basically control the barrier between the two, the grain and the source and drain. And at the bottom, you see the characteristic picture of the column blockade. So when the voltage which was applied here is increasing, now this is the voltage at the middle gate here, which was changing the potential, basically like a gate to the middle island. And this is a horizontal one. And the vertical axis is the top voltage, which was applied basically here to the source. Then as a function of 2 voltages, there was the origins of no current. You see the current scale is above, so the current was either very small, this is white areas, and red stripes is where the current was arising. And you see these regular stripes basically show us that there are regions of Coulomb blockades separated by lines of current. And if you go from one white stripe across the red stripe to the next white stripe, excuse me, then the number of electrons on the middle island, on the middle grain, is increasing by 1. So when you overcome the Coulomb blockade, there is a current, and then you go from the state of n electron, where n of course can be very large, to n plus 1 electron. And this energy which you need to overcome is simply the voltage which you apply multiplied by the electron charge. So you see very irregular stripes here, and then there are some also irregularities, some offsets, and this could be some parasitic traps or maybe phosphorus atoms catching electrons. Of course, there was not particular single phosphorus atoms. This was in a way kind of probabilistic preparation. So one of those phosphorus atoms was working, and the others maybe were catching electrons once in a while and producing a periodic response. So when the phosphorus ions were implanted, they of course sort of mechanically destroy the lattice. They go deep under the surface to a distance of about 15 nanometers, which depends on the beam energy, acceleration beam, which accelerates phosphorus ions. And in order to restore the crystal order around the phosphorus ions to make the crystal lattice regular and remove the disorder, one has to use here the thermal annealing. So basically, after the implantation, before depositing the metallic electrodes and forming all this device, the sample was annealed at 1000 Kelvin in order to repair the implantation damage. Of course, this is all probabilistic, but by increasing the crystal to the temperature of the crystal, you make the atoms move, and then they eventually occupy the lowest energy states, which are associated with the periodic lattice. So basically, these strips which are observed here, this increases the currents which are changed proportionally to the top voltage and the plug gate. They show that the single electron transistor works and can be used to manipulate small charges nearby. And then it turns out that they have seen small shift of the line of the blockade, as you see here around this blue arrow, and that's where they were doing the experiment shown in the next picture. So next picture that shows the energy level diagram for this device, which you again see in schematic form here on the left. So there is a source, there is a drain, and there is this central drain, which is called set single electron transistor island. And on the left, you see electron states which are located at the phosphorus ion. So these electron states can be occupied or not occupied. Of course, there will be only state for one electron, but this electron can be either spin up or spin down, depending on this is probabilistic. So, and this electron can come simply by tunneling from the small island into the phosphorus from the surface into the bulk. And then the two energy states, which are associated with the spin up and spin down state of electron, which is trapped on the phosphorus ion, are shown here on the left diagram as red and blue line. So these are the two energies of the two. Mu is the Fermi level, or if you want, electrochemical potential of electrons in the island. And clearly, if we have an electron here sitting in the island, and the green states are the electron levels in the island, then this electron can tunnel from the from the middle island to the left, and then can occupy one or the other state, depending on the spin of the electron. This could be one or the other state. And then one can measure, in principle, the state of this electron by applying a small voltage between the plug gate and the island. And basically, by lifting the energy level such that the spin up state will be above the Fermi level in the grain, and the bottom spin down state will be below the Fermi level in the grain. In this case, the red state will tunnel back to the grain and will change the current in the transistor, while the state with the spin down will not tunnel, and this kind of increase of the current from the transistor can be used as a readout. So basically, this is shown in the diagram below. This is the gate which you apply. This is a pulse gate where short time pulses are applied. When the voltage is at such configuration as shown above, then there could be either pulse of current or no pulse of current. And if there is a pulse of current, then the phosphorus atom state was occupied with a spin up electron, and if there was a phosphorus spin down state was occupied, there will be no current occurring in the measurement. So basically, first one need to load the electron with unknown spin into the system, and then by applying an additional pulse gate, one can actually determine which spin state it was. And in the readout, the spin down state stays at phosphorus, and spin up state tunnel to the set, which is followed by, of course, by tunneling for another electron with unknown spin back to the phosphorus. So the last thing, of course, can be done if we apply larger pulse amplitude, and in this case, the spins of either state will tunnel out to the grain, and there will be current pulse. And by using this technique, by using this pulse manipulation, the spin state on this individual phosphorus ion was measured directly, and they measured huge lifetime of the state. They measured about 30 seconds single spin state on the island. Of course, they didn't measure the T2 time in this experiment, but this, of course, requires more sophisticated manipulation. Now, this result is shown on this picture. I think I just, for the sake of telling you a little bit about other techniques, we'll go forward. But basically, if you look into this paper, which is a kind of seminal paper cited by many people, you could learn about this experiment where they were able really to detect this individual spin state on phosphorus ion. Now, very recently, same group in the year 2022, they have done an experiment with 2 trapped ions, and this really took them another 12 years to get to this stage. And they were able to demonstrate 2 qubit gate fidelities of almost 99%. This is a really remarkable achievement, which was really very required a lot of work. However, it still remains to be seen if this technology using spin states of donor phosphorus ions or atoms in the silicon lattice, if this could be still scalable. So basically, this technology is there. There are experiments which really demonstrate it works. So it can be scalable, at least theoretically, but you have seen how long time it took really to implement 2 qubit gates. And only recently has been reported this high fidelity 2 qubit gate using the system. It has an advantage because it uses the conventional nano fabrication technology. It has full electrical control, high coherence times. However, the requirement here is that you need to place the phosphorus ions with very high accuracy. So this can be done with maybe with a focused ion beam, but making this process not probabilistic but deterministic is really difficult. The other problem which exists in all the small nanoscale electric devices is that there are parasitic charge noise sources on any chip. So any semiconductor device, like a transistor or superconducting devices, small size, or mechanical devices, they suffer from parasitic electron traps on the surface of circuits. Most of these traps really occur on the surface and can be due to the residuals of the fabrication, like residuals of the resist. They can be due also to absorption of various gases from the atmosphere, like oxygen absorbed on the surface and so forth. And this parasitic noise, they really lead to small fluctuations of the fields around, and this in turn leads to dephasing. So one really has to use special pulse sequences, like for example the spin echo sequences, or maybe even high order speaker refocusing pulses, in order to compensate for low frequency fluctuations. And of course, these spins are also subject to influence of other defects, and the role of these sources of the coherence in large circuits still remains to be unknown. So I would say that currently this field is at the stage where superconducting field and ions field were maybe 15 years ago. So 2 qubit gates with superconductors were demonstrated around 2006, 2007. So here the whole thing was still in the rudimental phase, but now they all can also show high fidelity 2 qubit gates. Well, we'll see. So time goes and miracles become possible. Any questions to donors on silicon? All right, let's go on. Next example of impurities-based qubits are qubits in diamond. So these are the so-called NV centers, and they occur in diamonds as kind of generic defects which occur in the crystals. As you know, diamond is the hardest material in nature. It's all made of carbon, and carbon atoms are packed in a dense fashion that they are, each carbon atom has 4 neighbors. So this is really the hardest natural material. So the crystal structure is face-centered cubic structure, and there are 4 I mean, if you look into this order, of course, you need to kind of imagine that there are 4 atoms in the unit cell, and then you sort of multiply this unit cell according to the symmetry of the face center cubic lattice. Now, the defects which occur in diamond make the material diamond as a material not fully transparent, or at least give some color. And natural diamond, which is found in mines, can also have different colors, and this all depends on the type of impurities. So the impurities can be nitrogen, can be boron, can be other type of impurities. If you take the diamond and place it in the source of alpha radiation, the heavy nuclei of helium, then this actually diamond gets green color, for example. So all these colors are mostly not desired for high quality diamond, which is used for jewelry industry, but some of them actually are quite rare and therefore are valuable. For us, it's not so important. For us, it's important that the diamond has a really very large band gap, so it has a factor of 5 or more larger than semiconductors, so it's really very good isolator. And if there are states inside this gap of some impurities, the states can be manipulated by light. So one of the typical defects which occur in diamond is the so-called NV center. NV is abbreviation which stands for nitrogen vacancy center. So imagine that you irradiate diamond with some high energy particles. This could be, for example, nitrogen ions, or could be also something else. Or you could, for example, put the nitrogen, put the diamond piece into nuclear reactor and then add some nitrogen atmosphere, and then high energy particles will destroy some of the sites in diamond, and then the sites can be occupied by nitrogen atom. So imagine that you have a regular lattice from which you took away 2 neighboring carbon atoms. And then instead of placing back 2 atoms, you placed back only 1 atom, which is a nitrogen atom, which is slightly larger than carbon, and therefore the neighboring place near the nitrogen stays unoccupied. So there will be basically a vacancy situation. How to do it is, as I said, you could, for example, bring it into the nuclear reactor, and then you need to anneal, to heat it up to high temperature, and then all the defects will diffuse away. And then if you do it right in appropriate temperature, then most typical defect which will stay will be actually a nitrogen, which will come in because you could do it in nitrogen atmosphere, and a vacancy, which will form kind of bound state to this nitrogen. So, and then the material has the lowest energy state when the 2 electrons are getting trapped and form a quasi-pair around this defect location. So there will be basically 1 electron localized at the nitrogen atom and 1 electron localized near the vacancy site. So we know a lot about this because these kind of defects were discovered more than 20 years ago, or even more, in spectroscopy. And then the theory of this kind of defects was actually coming out from calculations using the well-known model for condensed matter physics, the linear combination of atomic orbitals, and also using the group theory based on crystal symmetry associated with this kind of defects. And if you make many of those defects, of course, you can observe them by using, or you can detect them by using the electron spin resonance. In Russian, it's called electronic paramagnitный resonance, actually discovered in Kazan many years ago. And basically, these defects have particular signatures which can be then detected in experiment. And of course, for this, you need many defects. So now, unique property of this defect is that it has a very well known and understood level structure. So it has the property of having effective spin 1 system, not 1/2 spin 1, because you have 2 electrons, one on nitrogen, the other one on the vacancy. And this is a resulting kind of spin state, because altogether there are 6 electrons involved into this spin 1 state. And of course, discussing all these details is a separate lecture course, which I'm not going to give here. Actually, I'm not really a specialist there, but just to give you an idea that you have here the singlet and triplet states of this spin system, spin 1 system. And the triplet state with the lowest energy is the superposition state, which is shown here. This is the state which is called lowest energy state 3A. And this is the ground state which has no spin because it's superposition state, but the 2 excited states of the same group are separated by small energy by few micro electron volts. And these are the spin up and spin down states, which are shown here by 2 arrows up and 2 arrows down. Now, above that, there are also states which are separated by large energy, and these are the states which you could excite by optical transition. So if you send high energy photons, basically laser light, to the system, then you can excite also similar states, and there are transitions between those groups of states. I will talk about them on the next slide. Now, there is a little splitting between spin up and spin down states. And the splitting occurs due to the so-called crystal field, which actually is due to the fact that the electron orbitals are slightly distorted by the crystal lattice. And therefore, there is a splitting also at 0 magnetic field. So even at 0 magnetic field, you have a splitting between those 2 spin states. And in addition, you can, of course, control the spin states by applying the external magnetic field by introducing the Zeeman splitting. So in a way, this system is very well controlled, and there are transitions here in this convenient frequency range, which is about, this is between the ground state and those excited state, which are slightly split. So these are in the range of 2.9 gigahertz. Of course, you can also modify these states by applying mechanical strain. You can apply electric field and so forth, but this I'm not discussing here at this point. Now, when you apply light, then optical transitions are allowed for the change of the spin number equal to 0, so for non-G spin numbers. And there is a strong fluorescence which comes out when we go from the excited states to the ground state, which occurs at 637 nanometer, which is in the red part of the rainbow, and the intensity depends on the spin state. So there are some intense transitions and less intense transitions. And then basically you can manipulate the qubit state by microwaves. For example, you can encode the qubit into the lowest energy state and one of the spin states, or if you want in between the 2 spin states and so forth. And then you can read out them by laser. For example, if you apply the laser pulse, which populates the high states, then you will see the fluorescence of the particular intensity for a given state. And also there are some long-living state, metastable state 1A, which is populated because of decay with the change of the spin number state. So the excitation of the system to the visible fluorescent state can be achieved by pumping with off-resonant lasers. So basically you pump with this very large energy, and then some small energy before you get to those states goes into the phonons and other excitations in the system. And then those states here are occupied, and then the fluorescence can be observed. Now, the qubit initialization can be done by spin polarization, basically by pumping this to high energy state and then corresponding relaxation. So you'll prepare some of the lower states here in the desired fashion. And then the technique of doing the measurements will be basically applying light pulses and microwave pulses to these spin states, to individual defects. Now, question is, how would we observe these individual defects? And this is really a very beautiful part of this technology here. The NV center is a single photon source, and it can be detected by using the so-called confocal microscopy. So in this case, you focus the laser beam not only in 2 dimensions, but you also make the focus in 3 dimensions, basically by choosing the focusing at a particular distance from the surface of the crystal, and then changing this focal point along the beam propagation direction. And then the setup involves the green laser, which is high energy, which you use for pumping and initialization of the qubit. This is green laser here, which is coupled here via the beam splitter. And then there is another beam splitter, which splits the beam into 2 locations with photon counters. So this will be the counting the photons as clicks, and the signature of second photon source will be that basically once the photon comes from here, it can either go to the right or it can go to the bottom. So only one of those detectors will click. On the picture on the right, you see actually ions which were, the defects which were implanted using the focused nitrogen ion beam, and then annealed, and then you see here that individual defects, they show fluorescent response. You can control this, of course, by microwaves, as I said, and also by magnetic field. I should mention that pioneers of this field were 2 physicists from Stuttgart. This is Jörg Wrachtrup and Fyodor Zhelezko, actually scientist who is now professor in Ulm, and his background is in actually he comes from Belarus, by his education, and has been working in Germany for many years. So basically, how can we see that this is a single photon source? We need to measure the autocorrelation function. So basically, if we have now these 2 detectors, and we measure the signal from those 2 detectors as a function of delay between the measurements, then once the photon comes from the single photon source, it will either make the upper detector click or the bottom detector click. They can never click at the same time. And that means that the autocorrelation function, which we'll measure, will be depending on the time delay between the clicks. And if the delay is 0, then there will be no correlation at all. Basically, this means that there will be always one detector clicking or the other. However, if the delay is longer than a particular time, which is associated with the propagation path and also the intensity of the source, then the function actually goes to 1, and there will be independent, basically, clicks of those detectors. So single photon source actually can be recognized if this autocorrelation function is square is actually smaller than 1/2. And this is real data from the paper of Fyodor Zhelezko back many years ago, showing that this is really a single photon source fluorescent from atomic scale defect. It's interesting that if you use optics to detect or to observe some small objects, of course, you are limited by upper limit of the microscope. You cannot really do it better than the wavelengths. But once you have a single photon source of sufficiently high intensity, then of course this single photon source, while its size actually is an angstrom size, will nevertheless allow you to observe these individual defects, and you can recognize them as single photon source by measuring this autocorrelation function. That's really kind of beautiful technique showing the individual atomic systems emitting light. Now, this is really a big field where the most applications are not in the field of quantum computing. Obviously, it's very difficult to put atoms, NV centers, nuclear vacancy centers, at desired locations and control the interaction between them. So I only mentioned this is a sort of part of modern quantum technologies, mostly used for sensing. And clearly, since you can detect the emission of light optically, you can measure very precisely very local magnetic fields, because the splitting between the energy levels, this fine splitting between the spin states of an electron at the NV center will depend on the local magnetic field. And therefore, you could apply microwaves, scan microwave frequency, and then basically measure the optical response. This offers an opportunity, for example, of measuring very local magnetic fields for very tiny objects. So one can make, for example, nanodiamonds at the tip of the scanning tool, and then image local magnetic fields of very tiny, also biological objects. The resolution of this magnetic imaging is not as great as, for example, for squids and whole center sensors and so forth, but the advantage is really having very high spatial resolution. So not the field sensitivity, but spatial resolution is really amazing. Now back to quantum computing, one of course can use the spin resonance technique to manipulate the spins. One can name the states with zero spin and non-zero spin as the two states you want to manipulate. And this is what is usually done in electron paramagnetic resonance or electron spin resonance. So one can initialize the system by laser, then observe the occupation of the state by fluorescence. And if you apply microwave, and then you have this resonant laser being your kind of measurement tool, then when you're occupying the state 2, there will be no fluorescence, and if you occupy the state 1, there will be fluorescence. And this shows the line which is observed in the bulk ensemble of the NV centers, and this shows also the energy splitting depending on magnetic field, which shows the spin states associated with this kind of defect. So one can measure, of course, Rabi oscillations there and apply increase the intensity of the microwave field. You see this intensity of microwave field is increased, and then the Rabi frequency increases. So this low frequency is A and high frequency is B. So basically all do this standard manipulation, but what is magic about it really that you could do it even at room temperature. So if you go to low temperature to a few Kelvin temperature or even below, then of course the coherence times improve, but still you can have very appreciable coherence of the order of few microseconds even at room temperature. So one doesn't really need sophisticated setup to decrease temperature, but rather use, of course, sophisticated enough to use those lasers, but operating fully at room temperature. And therefore, this was really a very attractive platform to think about quantum computing. Nevertheless, until now, it remains very difficult to scale the system up to make NV centers at wish at desired places and also make them interact. However, some of the computing techniques have been demonstrated there. This was done, for example, by using coupling of the NV center to neighboring spins. Now, let me say a few words about the decoherence of this type of quantum systems. Now, in natural carbon, there are also carbon-13 atoms, which are few, but they are always present. And to make isotope-free diamond, one really has to remove this, and you can imagine how expensive it will be making this diamond consisting primarily of carbon-12, which will be spinless. Now, there are also other isotopes of nitrogen. This also has to be paid attention. So nitrogen-14 has to be removed to avoid unwanted interactions of the NV center spins with the environment. Now, if one make ultra pure diamond, which can be synthesized from isotopically purified carbon, then the dephasing times increase at room temperature from a fraction of millisecond to several milliseconds. And if one really purifies more and more, of course, this time increases further to tens of milliseconds and more. This already would allow millions of gate operations, because the gates can be applied very quickly over time of almost a nanosecond, simply because the system is very unharmonic, and you could drive it very, very hard and make the Rabi flopping very, very quick. So the range at which these defects can interact without being distorted by impurities, of course, increases, but you need really to bring them close enough, and this people try to do by implanting, but nevertheless, having the separation of about a micron, which is feasible for implanting, still leaves quite small strengths of the interaction, which is still kind of unsolved problem until now. What was done in terms of quantum computing was a demonstration. This was already more than 10 years ago, done by the group of Jörg Kraftrup in Stuttgart, where they were lucky, basically having occasionally an NV center coupled to two carbon-13 nuclear spins. So basically they had 3-spin system. And by doing this, they were able to manipulate 2 of those spins in a fashion similar to a qubit. So they were able actually to make a 3-qubit entanglement in this experiment using the level structure shown below for 2 qubits. And they were able to form these Bell states, which is more exactly for 3 qubits are called Greenberg, Horn, Zeilinger. So this is a GHZ states. Don't mix it with gigahertz, but treats exactly the same way. On the so-called W state, which is written here, they were able to generate those states with relatively high fidelity and demonstrate elementary manipulations of this quantum information. But really going beyond these 3-qubit experiments, at least to my knowledge, there have been no success so far, while the people are still working and trying to implement those states. So my summary about these impurity states in nitrogen is on this slide. So the advantage is that coherence times, even at room temperature, are appreciably long. It's very efficient and convenient to read out these states by fluorescence, manipulate them by microwaves, prepare by laser pulses. However, to make the coherence really significant for doing the quantum computing, one need to remove unwanted isotopes, to remove unwanted impurity spins. At the same time, one can use this impurity spins as quantum memory, which is also an advantage, but still remains to be seen if it really works. Excuse me. Difficulties, as I said, is really to make multiple qubits and scale up. The coupling of the light between the qubits, of course, is a possibility, but as I mentioned, also when you go from laser beam in free space to the waveguide on chip, then efficient couplers are really still difficult to realize, and therefore it's difficult to couple this type of qubits to photonic waveguides. So it's still a lot of potential here. If you want to know more, there are many groups, including this group of David Ashalom, who is now actually not in California anymore, but in Chicago. This is still an old review, which is still relevant. Here you could learn more about this type of states. And in Russian Quantum Center, there is a group of Alexei Akimov actually working with this type of systems within these centers. So if you're interested, of course, he can tell you much more about that. Any questions about NV centers? Are you guys there? Was it too easy or too distant from you? Have you heard of this already? Can somebody answer?
So yeah, for me it was too distant and maybe too strange and too unusual. So yeah. I need time to think about it.
Do we have anyone who heard before about NV centers? Okay, so then I'm happy because I wasn't not intending to give a really in-depth introduction, and what you have got from me was really superficial thing just to introduce that. And I trust you will hear more about that when you talk about other quantum technologies in the following courses in your curriculum. All right, so this is the end of my slide series. Let me share with you another file. Meanwhile, you are welcome to ask questions if you have some.
А можно еще раз повторить, в чем разница между Т1 и Т2?
Да, конечно. Т1 – это время энергетической релаксации. Когда вы приготавливаете два состояния, одно из них имеет большую энергию, чем другое. Да? Ну, любые, в принципе, состояния почти всегда имеют разную энергию. Тогда существует процесс релаксации энергии, когда вы переходите из верхнего состояния в нижнее, излучая фотон в среду, в окружении. Вот это время Т1. А время Т2 – это время, когда вы приготовили суперпозицию этих двух состояний. Если 50 на 50, вы находитесь на сфере Блоха на экваторе. И дальше у вас релаксации, вообще говоря, как бы, предположим, что ее нет, но есть, вас дрожат как бы уровни, у вас меняется расстояние между уровнями за счет случайных внешних полей, за счет воздействия окружения. И тогда у вас состояние системы, которая есть стрелка Блоха, вектор на блоховской сфере, начинает диффундировать по экватору. И это есть время Т2. То есть это время дефазировки. Время Т1 чаще всего важно для приготовления состояния и для считывания, а время Т2 для манипуляции квантовой информации. Мы об этом говорили в первой лекции.
Хорошо. Понятно.
Okay, so let's continue with other examples of solid-state quantum systems, which can be used for quantum information processing. Do you see the slide?
Yes.
Yeah.
Okay, thanks. Okay, so in this lecture, in this part, we are going to talk about semiconductor technology and maybe a few words about some exotic subjects, but mostly about the semiconductor technology. So I told you already about ions, atoms, photons, about defects in crystals, which can be used also to manipulate and process quantum information. But now something which is really more close to electronics, about spins and quantum dots. Quantum dots. When you read the term quantum dot, quantovая точка, then different people think of different things. So there are, for example, this type of devices which have a size of a few nanometers, a few tens of nanometers, a few hundreds of nanometers. This is the so-called self-assembled quantum dots, which grow from gas phase on the surface of a pristine semiconductor surface, and then they form naturally kind of box for electron states, and then electron quantization in a box leads to discrete energy states, which are then forming the eigenstates of the dot. Sometimes people call the quantum dot a piece of carbon nanotube, which is actually which can be controlled by gates. And for example, you could localize electrons in a small fraction of the nanotube, and then operate it as a quantum dot as well. But most common are quantum dots, which are actually produced by electron beam lithography by lateral confinement. So you basically make a two-dimensional electron gas, and then you confine the electron gas in a particular area by using the metallic electrodes on the surface. And here there are many efforts which have been done around the world over the last 20 years or so to demonstrate quantum computing capability of this technique. So first we discussed the initial proposal, which was put forward more than 20 years ago by Loss and DiVincenzo. Then I will briefly discuss two types of heterostructures which are used to make quantum dots based on two-dimensional electron gas. I will explain to you the readout using quantum point contact and the spin manipulation with quantum dots, and then later on I think I have 2 slides about most recent achievements, what was done there. So imagine that you have a semiconductor, and as the first example we can take 3,5 semiconductor gallium arsenide. And you may already know from your electronics or from solid-state physics course, this is a kind of semiconductor which is being used in a variety of electronic devices. So as a matter of fact, these were structures which were most convenient to make a whole series of very beautiful experiments with low-dimensional systems, with two-dimensional electron systems, quantum Hall effect, and similar, and also the one-dimensional and even zero-dimensional systems. One-dimensional will be quantum wires, and zero-dimensionals will be quantum dots. And here, basically, you take the gallium arsenide as a semiconductor, which is basically a good isolator at low temperature, and then you dope the semiconductor such that the band structure will be banded near this doping layer, and then the Fermi level will be above the bottom of this very thin doping layer, so that there will be only few electrons entering a very thin layer, which is shown here in yellow. And then you cover this layer by so-called cup layer, based on the differently doped aluminum gallium arsenide, and then cover fully by cup with another gallium arsenide. And basically, by using the trick so that you make the electrons distance from your impurities, this would basically allow for them to move freely. People have managed to achieve very high mobility, and this high mobility devices are used also in transistors and so forth. So this is a very beautiful solid state systems to study low dimensional physics, low dimensional transport, and so forth. And the motion of electrons occurs in only 10 nanometer thick layer of electron gas, which is so thin that the electron states are quantized in the direction perpendicular to the substrate, in the vertical direction on this plot. And the reason why it's possible is that because the electron density in this electron gas is very low. And for low electron density, you can recall your knowledge of the Fermi gas. You would have relatively large, relatively low mass and relatively large Fermi wavelengths. So the wavelengths of electrons in these two-dimensional structures is typically 2 orders of magnitude larger than the Fermi wavelengths of electrons in the metal. So it can be as large as few nanometers or even a few tenths of nanometers. And thanks to that, due to the large electron wavelengths, it's delocalized, and therefore it doesn't really interact with impurities, can move freely and achieve very high mobility. So this is the principle of making the high mobility semiconductor heterostructures, which have been known for many, many years. I think all the physics of 80s and 90s of electron transport was done with that. And then you place on top metallic gates such that you could sort of push away electrons by Coulomb forces from the area below the gates. So by pushing away, you leave two-dimensional electron gas only in this location here. So they are pushed away from here and from there. So only here you will have electrons in two-dimensional electron gas. And then if you make this little island very small from other directions in this two-dimensional topology, then of course you have a quantum dot. So in a way, this is a solid-state version of an electron trap. And you can use the advantage that the electron wavelengths, as I said, the Broglie wavelengths of electrons is really, really large, so you could really operate them as waves here. And the quantum dots, for example, two quantum dot configuration is shown here. They could be a little area of the two-dimensional gas. This kind of green circle shows where the electron gas exists, and outside this area, the electron gas doesn't exist. And then there is a left dot and right dot. Now, these dots are so small that the states of electrons in the dot are quantized due to the spatial quantization. As I said, the wavelengths of these dots is large, and therefore the energy level separation between the individual states of electron in the box is also quite large. And that's why one can actually use these quantum dots as quantum states of electrons, which are specially localized. It's kind of little island with electron, which has advantage of having large extension, which can be controlled by the relatively macroscopic of few tens of nanometer scale electrodes. And also the spin states can be manipulated by magnetic field. And the proposal of using quantum dots for a quantum computer came up a really long time ago from Daniel Loss and David DiVincenzo, where they actually were proposing to use spin states in quantum dots to carry quantum information. The problem is that quantum dots, of course, carry charge, but as I said already in relation to defects, the charge is not a good degree of freedom because there are many sources of the coherence for the charge states. So there are defects on the surface, there are charge traps, there is a charge noise, and all the charges get decoherent very, very quickly. However, if you encode information in the spin states, which can be controlled, for example, by Zeeman splitting, then those spin states being different in spin but identical in charge, they will not suffer at all from Coulomb's random Coulomb fields, and therefore they can be manipulated by magnetic field, and the coupling between them can be varied by the split gates, which are often called as J gates. So in a way, it's similar to the Kane proposal, which came about the same time, same year. You remember Kane paper with this sketch was appearing in Nature in 1989, and same year in PhysRef A, this proposal appeared. However, here is much more, I would say, technically easy task, because you don't need to implant spins of phosphorus, but you basically form them, the spin states, on the surface of the two-dimensional electron gas. And this size here can be as large as let's say a few tens of nanometers or even 100 nanometer. So, and then in Kane proposal, electrons were only mediating interaction with nuclei. Here, you don't need to mediate anything. You work directly with the spin states of electrons on the dots. So basically, it sounds simpler, and it turned out to be really somewhat simpler. Nevertheless, it really was very hard and difficult way to implement all the required steps for demonstrating quantum computing potential with the structures. So initial proposal of Loss and DiVincenzo was considering using a wire as a source of magnetic field, and then magnetic field decays away from the wire such that there will be different magnetic field magnitude seen by the most left dot and then other dots and so forth. So magnetic field was decaying, and therefore the Zeeman splitting was decreasing from left to right. And therefore one can choose individual resonance frequency for different dots, which are located at different distance from the current carrying wire. And then one can basically apply the AC electromagnetic field to manipulate the quantum states, spin states of the dots due to the Zeeman splitting. The technologies which are used nowadays, actually, there are two. Initial technology was coming from semiconductor field, where the gallium arsenide was showing the highest mobility. More recent experiments, they involve different types of heterostructures, which are called silicon germanium heterostructures. Both of them have the virgin crystal. In the left case, in the case of gallium arsenide, is gallium arsenide. On the right side is silicon germanium. And then you have some layers which are used to form a two-dimensional gas. This is the aluminum gallium arsenide and then doped layer with a cup for the left structure, and then there is a silicon germanium, and silicon cup layer for the right structure. Now, this technology was developed a bit later. I think now they also can show very high mobility, but there is a tremendous advantage of silicon germanium heterostructures relative to gallium arsenide heterostructures, and this is due to the spin states of the underlying structures. For gallium arsenide, the natural mixture of gallium and arsenide consists all of nuclear carrying of isotopes which have nuclear spins, and while mitigating the results of these spins of the matrix crystal is possible, but really it limits very significantly the spin coherence of the spin dots. You have some random noise of the spins around of nuclear spins. And these nuclear spins, they act as the coherence bus, as a noise source for the electron spins of the dots. So you see all the gallium isotopes, which there are two actually, which are major abundance of gallium used in these gallium arsenide structures. They're both magnetic, and they cannot be spin carrying states, and they cannot be used as neutral medium. In contrast, silicon and germanium, they can be made of really isotope spin-free states, and the making isotopically purified silicon is a quite well-established technology in semiconductor field, and one can have technique to remove silicon-29 isotope to completely eliminate dephasing due to the nuclear spins. Therefore, this is much more promising technique using group 4 semiconductors rather than 3-5 semiconductors for this type of technique due to the role of nuclear spins. The fabrication of these heterostructures involves the molecular beam epitaxy, where one can actually, in very high vacuum, grows the crystalline perfect structure on the substrate, making atomic layer by layer deposition. And this requires very high vacuum, as I said, and very slow deposition rate. It requires also appropriate substrates to grow monocrystalline films. Now, this has to be done at high temperature because the high energy components which come here from crucibles on the right, from the fusion cells on the right, they come with a particular disorder, and then the self-annealing is achieved by growing the structure at high temperature. And the technique to control that is the so-called reflection high energy electron diffraction, RED, which is basically controlling the order of the structure while it grows. So one can actually observe layer by layer growth of the structure and monitor this, and then guarantee the highest perfection of the growth during the process. This is really very well established process, quite very expensive, of course, but really established in the world. And in semiconductor field, of course, there are always champion growers in different places where you could get the highest mobility two-dimensional electron gas structures. But that's something, of course, which I'm not going to discuss. It's like cooking, and there are Michelin star, 3-star cooks, and if you just come and start cooking without really having a talent and background, then of course you are not aiming to end up immediately in Michelin guidebook. So this is also kind of art, growing the structures, not just skill. The MBE machine looks like this. It's sophisticated. It requires really a lot of time and effort to make it work. And usually people who grow structures, they just do this. They just not do anything else. And of course, there are also some growers in Russia. This is like the field, even the field for itself. Anyway, suppose you have this heterostructure. You got this wafer with grown heterostructure in a good place with high mobility electron gas. Then you need to make the quantum dot. To do this, you have to use the electron beam lithography. And I'm going to speak about this also when I discuss with you the superconducting qubits. But just to give you an introduction, the technique is shown here. Basically, you use the electron beam, which is illuminating, which is focused on the thin layer of polymer, which is called resist, which is deposited on heterostructure. So you put some liquid with this polymer, then you dry this in the oven, and then you put this in the electron microscope or e-beam lithography unit with electron beam, and then you draw a line with electron beam. And electrons, they modify the bonds in the polymeric material of the resist. And then once you put this material into the developer, then the area where the resist was irradiated is removed. And basically here you have a line which forms a kind of gap between two pieces of polymer, which can be as small as the width of your electron beam. And typically in electron lithography, lines of the order of, let's say, 20 nanometers are possible. Then you evaporate metal from top, and then you put everything in acetone, and you remove this resist and the resist on the other side, together with the metallic layer on top. And what you are left with will be very narrow metallic electrode. So this is really something standard for semiconductor technology when one works with these low-dimensional transport structures. So this is the way you could make very narrow electrodes of the size which will be, let's say, down to 20 nanometers or so. And then you make a structure of these gates, such as, for example, shown here. So these are your metallic electrodes. You draw them with electron beam, and that's where your metallic film is located. And then you also need to make a contact to this two-dimensional electron gas and also to the gates. So top structures are called gates, and the two-dimensional gas is at some distance below the surface, as I already explained. So in this case, you have to deposit some metallic pads here, and then use some moderate heating to make the metal diffuse into the material of the two-dimensional electron gas and form an ohmic contact to the two-dimensional electron gas. And then basically you can connect your wires to the two-dimensional gas, and you connect your wires to the top gates. And that's basically standard procedure, for example, of making high mobility transistors or making structures for low temperature transport studies of low dimensional systems. And again, that's something which I already explained to you. So to measure the charge on a small island, you use here single electron transistor, something we discussed already today in quite some length. But now the structure is formed differently. So here the source and drain are big pieces of the two-dimensional electron gas on the left and on the right. And then this little island is a small area of the two-dimensional gas, which is isolated from the rest of the two deck by these electrodes, so that electrons can tunnel from the source into the island, and then from the island into the drain. And then this gate basically contains controls the potential of the island. And basically the single quantum dot can be used as a single electron transistor in a similar fashion to metallic transistor, which I described to you in relation to measuring the silicon phosphorus qubits. So by playing with these voltages you apply to these electrodes and playing with the shape, one can actually form an arbitrary shape of the potential, which has a lot of possibilities here. And then again, just sort of rephrasing what I already told to you, what you could do, you could fill the electron states in the island by making them tunnel one by one. And if there's a electron quantization states in the island, so basically electron in a box has discrete energy states because its wavelength is sort of comparable with the size of the system, and it gets states in the box. If you want, you can quantize it as a rectangular box. You know it from quantum mechanics how to get the eigenmodes, eigenstates for the quantum box. And then the electron can tunnel into the box from the source if a particular state is not occupied. Now, this is the Fermi level here, or the field states. These are the field states in the dot. And then if you bring the first state above the Fermi level below the potential of the source, then the electron will tunnel from the source. And if there is a drain electrode, it will also tunnel to the drain. So in this situation, there will be a conductance such that conductance will occur if the source Fermi level is above the electron state level in the dot, but that one is above the Fermi level in the drain. So in this case, you have conductance, and you have this peak in the current, as shown here, and you have Coulomb blockade if the state is below, since electron cannot tunnel in all the states in the drain electrode, they're all occupied. So you need to have some states above the Fermi level there. And again, once you further change the voltage of the gate, then you will see that this also states which is show tunnels, so tunneling will be blockaded. So in a way, this is really a device which has amazing charge sensitivity, can measure electron charges down to a fraction of a million. So 10 to minus 5, 10 to minus 6 charge sensitivity is quite achievable. And basically, a current of many, many electrons is reached only by the current of half electron charge. And that's why we actually can use this for these high sensitive charge devices. So this is the operation of the single electron transistor. And what you do basically, you apply the two voltages, you apply source drain voltage and you apply the gate voltage. And then you start from having no electrons on the dot. This will be this area and this area. And then if you cross this line in this diagram, then you have one electron in the dot. If you go further up, you have 2 electrons in the dot, and so forth. But then if you go horizontally, then you could sort of lock the electron inside the dot and then do something. And basically all these regions are characterizing different number of electrons on the dot are characterized by these peaks of currents, which are due to the increase of the tunneling current when we have a situation that the dot state is exactly between source and drain, and some current is applied between source and drain. So this leads to observation of the so-called diamond structures. And here on the diagram of the diamonds, you see here, for example, if you zoom, this is the differential conductance, okay? The dark area is where the current appears, and the red area is where no current takes place. And you see there is a large area when there were no electrons in the dot. This is this whole space to the left and into in down direction of this plot. But if you zoom here in this rectangular, then you see states with in the double dot. This is a double dot because you have 2 of them. So here you have no electrons anywhere. So both dots are empty. Here you have 1 electron in the left dot and 0 electron on the right dot. Because you applied particular gate. Here you have 1 electron on the right dot and no electron on the left dot. Here you have electrons on both dots and so forth. Now the most interesting, of course, is this area here. In this area, you see that you have a small joint between 0, 1 and 1, 0 state. And that's where an electron can tunnel from left dot to the right dot and back. And if the electron remains coherent, it can actually form superposition state, like in the double well potential. And this can be manipulated as a qubit, just as an example, of course. So this type of states have been, of course, manipulated, but remember now the charge states are not coherent. We need to come to be able to control spin states. And spin states can be generated by removing the degeneracy with applying magnetic field. So you apply magnetic field, and then spin up and spin down states have different energy, you have Zeeman splitting. And basically, if you control now the gate, you move the Fermi energy in the dot up and down, then you could make it possible to tunnel from the spin down state and not have any occupation of the spin up state, for example. So depending on the separation between the two states, you can manipulate now with source and drain and gate, and basically distinguish different spin states. And this is, I'm not sure if I have a picture later on, but this basically will lead to the splitting. So all these lines now here will be split in two lines or two spin directions. And then one can select between different spin directions and manipulate between different spin states. Now, how to measure the electron states on the dot? And one of the possibilities is to use the so-called quantum point contact. So quantum point contact is basically a one-dimensional channel, a narrow channel in which only few electron states, quantum mechanical electron states are possible. So basically, you make, imagine that you have electron wave function, the electron is moving in the two-dimensional gas. And then you confine the quantum point contact into the area, which is so small that the electron wavelengths gets quantized in the direction across the channel. So you have 1, 2, or 3 bands, or if sometimes people call quantized channels of the electron transport through the dot. Basically, if the dot is smaller than the electron wavelengths, the wave will not go through. So if you have the wave which is seeing a hole smaller than its wavelengths, it will not go there. But if you make the hole a bit larger, then there could be propagation of the wave if the hole is half wavelengths, or it is 2 half wavelengths, or it's 3 half wavelengths, and so forth. So basically, it's quantization of electron state to electron wave function in transverse direction to its propagation. And this is the quantum point contact, which has quantized resistance. This is beautiful work done in the 80s by Bart van Wies and the others. And the station is really, this really led to amazing progress with low-dimensional structures in the 80s and 90s. So one can use a quantum point contact, which is basically a narrow gap between two metallic electrodes. You can control the width of this channel by applying a voltage to this quantum point contact gate. And then electron wave, which will propagate from, for example, from source to drain, will be very sensitively influenced by the fact if there is an electron in the dot or there is no electron in the dot. So the electron present in the right dot will have larger electric field effect on the quantum point contact than the electron present on the left dot. And therefore, by looking into the change of the current in the quantum point contact, which is this device here, one can distinguish if the electron is on the left or electron is on the right. And this is the technique of the projecting the states of superposition states of electron, which is tunneling between the two dots, on the localized states in the individual dots. Once you measure with the quantum point contact, then you would be able to tell where the electron is. Of course, you could also imagine here doing very weak measurements, but this is, of course, a kind of separate subject, which we are not going to enter now. All right, so the quantum point contact is known to show its plateaus of conductance, and each conductance change conductance is the inverse resistance. So basically, the conductance quantum is 2 square of electron charge divided by Planck's constant, and this conductance the quantum is actually can be measured in also in variety of low-dimensional transport experiments done in the 80s. These are really beautiful works. If you don't know them, really very instructive to have a look there. So you can have 1 electron channel in the quantum point contact, 2 electron channels, and so forth. And well, I wanted to show here that these channels really exist, and people have been able to scan the cantilever of atomic force microscope to measure the local electric input. Actually, if you influence one way or the other channels, there is a change in the current, and people were able to visualize these channels in the quantum point contact. It's not just magnetization as a secondary demonstration, but also direct indication of the presence of this channel, those low dimensional transport channels in this low dimensional structure. Now back to the qubits. So people will see then a small change in the current in the quantum point contact if the electron tunnels from left to right. That's what I told you. The charge sensitivity of this particular experiment was not terribly great, but was sufficient to detect the coherent oscillations of the electron. It was about 10 to -5 electron per square root of hertz. And skipping the details, I can only tell you that, well, basically, this was what was observed in this experiment back many years ago, that the electron going from spin up to spin down state was split by the Zeeman energy, and then by applying short pulses, people were able to measure not only spectroscopy but also Rabi oscillations of the electron in this double dot, and also to measure the spin relaxation time, which turned out to be quite appreciable of the range of milliseconds at low temperatures. And this shows the resonance spin control. When you increase the amplitude of the AC signal, these are Rabi oscillations. So as you see, the frequency is changing here. So again, we talk here about Rabi flopping between 2 states and then measuring the projection on the individual state of the dot. Now, they were mentioned that charge qubits are not really favorable because of the charge noise, but these experiments have been also done showing very limited coherence, only of the order of a nanosecond, which is really tiny compared to the millisecond observed for the spin states. And the origin of the coherence in quantum dots is primarily the environment, which consists, of course, of the lattice having the magnetic spins of the nuclei. It has also spin-orbit coupling due to the other degrees of freedom. It has also fluctuations of the external field and further factors of the coherence. So there is plenty of the coherence factors which occur there. Now, there was a remarkable experiment done a few years ago where people were able actually to demonstrate 2-qubit gates in silicon germanium quantum dots with a coherence of the order of microseconds. And more recently, there were 2 papers in Nature, actually published back-to-back with the paper of Morello group, which I mentioned earlier today, where they were able to demonstrate 2-qubit fidelities of the order of 99.5%. You see these diamonds are really very clean, and I'm skipping here the detail, but you see the degree of sophistication of this experiment. These color things are metallic electrodes, and this is, I think this is a micron here. I mean, no, this probably is 100 nanometer bar. And yeah, this is really very advanced experiments, requires a lot of nanofabrication, a lot of patience in tuning up the voltages and then finally operating this device. But nevertheless, it's doable. There are 2 papers, as I said, published back to back very recently, and there is a very nice news and views in Nature on the perspective of spin qubits and quantum dots. So I think my time is up. This is my summary. So the quantum dot technology is very promising. of course, because it uses semiconductors, it uses electric control, but really quite sophisticated because one needs to use a lot of electrodes to tune the whole structure into the working points. The dephasing times are not really that long. And one needs to scale to many qubits now, though for simple circuits of 2 qubits, very high fidelity gates have been already demonstrated, but this is something again, which when compared with superconductors and ions, is like 10 years back. All right, I think I'll stop today, not talk about all about helium. This is really kind of a little detour. Thanks for your attention, and please ask questions if you have any. I would love to have questions.
У меня есть один вопрос.
Да?
Правда, это немножко глупенький, наверное. А я немножко не уловил. А вот что используется в случае квантовых точек в качестве кодирования состояний конкретно?
Значит, в квантовых точках существуют дискретные уровни энергии для электронов. Это, наверное, поняли, да?
Да.
Вот. И эти уровни энергии, они, значит, соответствуют, значит, на них можно воздействовать, значит, электрическими магнитными полями. Значит, если мы воздействуем электрическими полями, то у нас, соответственно, эти уровни энергии меняются очень сильно, и это как бы есть состояние зарядования, то есть charge qubit. А если мы теперь с вами приложили магнитное поле и расщепили одно и то же состояние зарядовое на 2 спиновых, так, то это состояние, оно иммунно по отношению к зарядовому шуму. То есть зарядовый шум будет одинаково действовать на эти 2 расщепленных спиновых состояния. Поэтому для вот высококогерентных квантовых точек используются вот эти дискретные уровни, но которые возникают которые возникают при одном и том же количестве электронов на квантовой точке, но с разным направлением спина, то есть spin up и spin down. Используется дискретное состояние, значит, электронов вот в этом маленьком объеме, которые соответствуют одному и тому же числу электронов, но при этом расщепление создается магнитным полем за счет Зеймановского эффекта.
Понял, спасибо большое.
Угу. Еще вопросы, пожалуйста. Хорошо, ребят, значит, мы тогда с вами расстаемся на 2 недели. Как я говорил, на следующей неделе я не смогу читать лекцию, потому что буду в самолете. Надеюсь, что все будет по плану и прилечу в Москву. Вот. И через 2 недели, надеюсь, вас увидеть воочию, вживую в квантовом центре. Вот. В это же время во вторник, в 10:30. Хорошо, спасибо за внимание. До встречи.
Спасибо вам большое.
Спасибо, до свидания.
Спасибо, до свидания.